Okay, you guys can hear me and see my screen?
Yes.
Yes.
Okay, good. Good morning, everyone. Thank you, Dr. Deb, for the introduction. So I'm Dr. Muztaba Fuad. I'm a professor of computer science. I've been working as a faculty fellow as part of CADS. I was working, I'm in a broad sense, I'm working with mobile crowd sensing. So if you remember from last year, last symposium, I gave an overview of the research. So this time when the time come for me to present, I say, okay, let's share one aspect of that research, and I'll try my best to explain something very technical, and that way you guys can see how nerdy we computer science folks are. Okay. Anyway, a little bit of update. So mobile crowd sensing is a very wide topic. This presentation is one aspect of that, where we are using the Bluetooth signal strength to figure out mobility in an indoor space. We already secured a NSF grant for that, and we have one publication already accepted in a conference and one in the pipeline for a journal. And one of my graduate student, Briggs John, and our CADS research associate, Charles Mikkel, actually helped me, along with, of course, Dr. Deb, in this research. Okay, so what is the need? Why want to do something I'm presenting? So the biggest idea came from the collaborators from physical therapy department, where we know that there are a lot of waste in the healthcare system. There are a lot of different research, a lot of different approaches going on to solve that waste. One of the cases of that waste is inefficiency. So how can we be more efficient in the clinic, and what we can do? So one of the solution is how can we make the clinic layout more optimized, so that as the clinicians are moving among the clinic rooms and between the furnitures and the instruments, they are more optimized in movement. One way to solve that was to let someone observe the clinicians, but it's found out that it's not productive, it's subjective, and sometimes it's inaccurate. Okay, so if we somehow can find the mobility patterns automatically, then we can make it more productive and more accurate. That's the whole idea of this research. So that's where the mobile crowd sensing comes in play, because we want to do opportunistic crowd sensing. Means remember, all the clinicians have a mobile device that they are carrying all the time. We want to sense that device and use that to see how they are moving around within that indoor space in the clinic. We can, I know obviously some of you have a question about privacy, so wait for that at the end and ask me that. We'll surely discuss about that. Along with that, we can also get some contextualized information, like whether there was a fall, or so many other things we can get from the cell phone, and we can combine that and then can use big data analytics and visualization to make it more automated and more productive. That's the whole idea of this research. So for this aspect of this research, we are using Bluetooth low energy technique. So normally, traditionally, other researchers use a dedicated hardware. They're called beacons. So what they do is they will put those in the room, in the indoor space, a couple of them around the space. They are very small device that runs on those CR32 batteries. They don't have enough computational power, and they don't have actually any computational power. They just sense the data and send it and upload that to cloud. and then you need to download it from the cloud and do your processing. So one aspect of this research is also data redundancy. So we don't want to do that. We want to make those sensing node more powerful. So that's why we moved away from that beacon, and we want to use the technology that already cell phones have, and that is being used successfully during COVID for the contact tracing. You can sense your proximity and see who is around you, and that way you know who to contact in case you know there is an infection. So I went through a little bit of that. There are big two difference, as I mentioned, with all the related research. One is we are using sort of like the proximity measurement, and we are not using any specialized hardware or software. Okay. But it's a thriving area of research. There are a lot of research going on in this area, because for so many, if you go outside, you have GPS, but indoor you don't have GPS. So, and there are a lot of research going on to figure out where you are. So let me quickly give you how long I have, not that long. Quickly give you the experimental setup. So assume that we have, in a clinic 3-room where we placed 3 stationary mobile devices in red, as you can see, and we have a mobile device which is moving. We wanna figure out its movement in the indoor space. Okay. So what happened is, assume this is right now the situation is the mobile device, the blue moved from stationary device towards the stationary device 2, and you can see in the dotted line that's how it's going to move in the future. So our goal is to figure out a path that will show that moving device actually came from started from stationary device 1 and went closer to stationary device 2, and then to stationary device 3, and then eventually it stopped at stationary device 1. Okay, if we can figure out that path automatically, hey, we don't have to have a human proctor to notice and being accurate or subjective and all of that. We can figure that out automatically. That's the whole idea. Now, each of those stationary device and including the moving device has a radius of proximity, like it can sense any device within that with any Bluetooth energy, the signal strength. That's called the RSSI, Bluetooth signals indicator, strength indicator. So as soon as a device moves into that radius, it can sense that, and it records that signal strength. So to explain that, what this algorithm does is it checks, it collects the signal strength of a device as it's inside its proximity, and then the gradual change of that signal strength. So assume that the 2 stationary devices, and those are their radiuses. Currently the device is in the blue position. So at that position, both stationary device 1 and stationary device 2 will sense a specific power level, a specific signal strength that the current in that current position, that the mobile device is has a there is a proportional relationship. If the signal strength is big, that means the device is closer. If the signal strength is less, that means it's further away.
We have about 3 minutes left.
Okay, thank you. So by sensing that, if we are sensing that device every so frequently, we'll get all those data from the device in the past and in the future. Okay, so after a while, we'll get something like that. Once you aggregate all the data, where it shows every timestamp and each stationary device power level for that one device. Okay, and you can put them in a table, and then you can run the algorithm that we devised, that I'll try to explain in real quickly. So this is what happens once we have the aggregated data. We sense the data, we put it in a table form. We first sort that by time, because we know starting from here and up to there, and then we pick the device which has the strongest signal is the starting point of the path. Obvious reason, because the bigger the number, the closer the device is. Similarly, the largest device which has the device which has the largest signal strength at the end is the destination. So once we figure out this is the source and this is the destination, what we do is between every row we check the value. If the value changes from bigger to smaller, that means the device is moving away. And if the device, if the signal strength is becoming smaller to bigger, that means it's coming towards, because that's the proportional thing is. So once we have that, we are doing that, we're creating vectors. Each vector has a source and a destination, a head and tail. So next we look at those head and tail, and we started merging them with one another, and then we will get a path, a sequence of stationary devices through which this mobile device is moving in that indoor space. So along with that, we are also doing a couple of other things. First of all, our goal is to do data redundancy with beacons. You can't do that over here. One of the stationary device actually process all those information, the aggregation and all of that. We call it header. So whichever device goes in the system as the first one, that's why we call it first in first serve algorithm, it becomes the header which aggregates the data and figure out the path, and then only the path is uploaded in the cloud. So that way we are saving data and processing and all of that. Okay, so once we run the data, so I have 1 minute probably, or 30 seconds. Okay, so we run the algorithm on two different sets of data. One is the simulated data, and one is a real experimentation. We walked around with a mobile device in front of the CAD center in the New Science building, and we measured the data. As you can see, the left one, the person was working from stationary device 1 to 2 and then to 3, and the algorithm successfully show that. On the second one, the person moved from S1 to S2, back to S3, and then back to S1. As you can see, the algorithm show it from S1 to S2 to S3, and then S2 and S1. So for obvious reasons, we already figured out why that is. In the simulated data, the first one, the data is perfect, but in real life data is not perfect. There are a lot of noises. So that's what the right hand side is. Even when the device is between S3 and S1, S2 sensed some. Okay, so this summer we'll be working on that, tuning it, figuring out how we can distinguish that. Okay, so I hopefully you have a question other than privacy that comes in first, but I just want to thank that the NSF fund and the CADS fund that helps us working on that. So any question?